In this video, we're going to be doing a free fall kinematics problem where a person is throwing an object 10 meters per second upwards off a 12-meter platform, and the second person is throwing something downwards at 10 meters per second off of that same 12-meter elevation point. So what we're going to do is we're going to solve for the final velocity and the total time in the air for both of them. Now, in order to do that, we're going to need our three accelerated motion formulas, which you see in green at the top of the screen. And we are also going to need three known variables. So for this one, if we're throwing it upwards at 10 meters per second, we know the initial velocity is 10 meters per second. And we also know if something is in free fall, the acceleration is always negative 9.8 meters per second squared. And in addition, because they're elevated 12 meters off the ground, the displacement of the actual object is going to be negative 12. And I'm going to call that delta y because it's a change in a vertical position as opposed to a change in a horizontal. Okay, so now we have our three variables. So what we're going to do is see which one we can solve for the final velocity. And the first one has final velocity in it, but we do not have time. So let's go and find another one. The middle one does not have a VF, and the last one does have a VF. And we have VI, A, and the delta X, or as I said, in this case, the delta Y. So let's go ahead and plug into this third formula and then see what we get for our VF. All right, so I plugged in all of my values and I have 10 squared, which is 100. I took the product of these three numbers and then summed them up together, and I got 335.2, square root of both sides, and we have a VF of 15.34 meters per second. Anytime we take the square root of something, it's always basically plus or minus the value, but because we know the object is going to rise up and then fall down, the final velocity should be negative. So this one won't naturally come out with a negative, but since the object is going downwards at the very bottom, we're going to have to include the negative ourselves. All right, now let's go ahead and solve for the total time. We have two formulas with time in it. The first one over here is definitely going to be a little bit easier to plug everything in. So let's go ahead and plug in all of our values into this first formula and then solve for our t. All right, so I plugged everything in. I put in my new VF minus the VI divided by t equals the acceleration, and I basically just cross multiplied the negative 9.8 and the t. Those switched spots, so then we had a negative 25.34 as the numerator divided by the negative 9.8, and I have a total time of 2.59 seconds. All right, so that completes the first two solutions for finding our VF and our t. And we're also going to find those same two things for our second one. Now, the difference is going to be now that the 10 meters per second is directed downwards, our VI is going to be negative 10 meters per second. Our acceleration is still negative 9.8 meters per second squared for anything in free fall. And our delta Y is still going to be the same. The object is being displaced downwards 12 meters, so we have a delta Y of negative 12 meters. So I'm going to go ahead and take a little shortcut because I am doing very similar calculations. We're plugging in all of these same numbers. The only difference is the negative sign for our VI. So that will take care of this new type of motion, just adding that one negative sign in right here. So that is very significant. So if we take a look at our equation orange over here, we are going to have VF squared equals negative 10 squared plus 2 times negative 9.8 times negative 12. Okay. And if you do 10 squared, like we did the first time, or negative 10 squared, you're still going to get 100. So I can already tell that my VF is going to come out to the same exact number, 15.34 meters per second. And because we know that the object is going to be moving downwards at the very bottom, we're going to have to place that negative in ourselves, and we're going to get the same exact answer. Now, some people might wonder, why would we get the same answer? Because this one is being thrown upwards, it's rising up, it's going to fall down from a higher peak, and it's going to come back down, and then it's going to fall that 12 meters. This VF right here, just getting that straight um, velocity downwards, and then it's going to hit the ground. The reason why they have the same exact final velocity is because if you throw something up at 10 meters per second, once it reaches the ground level to where it was tossed, it's always going to be the negative version of that initial velocity. So although it's thrown up at 10, by the time it rises up to its peak and then falls down, it's going to be going negative 10 once it reaches the point at which it was released. So both of the scenarios have the object moving down at negative 10 from its release point eventually, and then they fall an additional 12. That's why I have the same exact VF, which can be confusing to people once they get that result. Now, for the second calculation, it's going to look very, very similar. It's going to be the acceleration equals the VF minus, and this time a negative 10. So you're basically going to be adding them together, which would just give you 5.34 in the numerator divided by the negative 9.8. So once you take those two and switch them, your time is going to be 0.54 seconds, which is significantly shorter than the first time, because the first time the ball has to rise all the way up to its peak, fall back down, then come back to its original release point, and then fall to 12 meters. So the second one, it just got thrown straight down towards the ground. So it does not arc up and down. So its time is going to be significantly shorter, which it is. So to sum things up, when you're working on a problem like this, you want to make sure you draw out as much visuals as you can so you recognize which parts are negative and positive. And then from there, this happens to be a special case where your VFs end up being the same thing because of the concept that your VI and your VF will be the same number but different signs as long as the object is coming back to the same level. So this 10 went up, came back down as a negative 10, and then started off just like this one did right over here. And then as far as our times go, our times are significantly different because the first one had to rise and then fall, and the second one just shot straight down towards the ground. So I hope that was helpful in helping you solve a free fall kinematics problem. Thank you very much for watching and listening.